Welcome to the Deep Dive. We're going deep into the world of cybersecurity today, exploring brand new research, straight from the source, RCIF.
Oh yeah, Archive, the online hub where scientists post their preprints before official publication.
Exactly. We're talking fresh insights, the cutting edge, maybe even a glimpse into the future of digital security.
It's like peeking into the labs and seeing what's cooking before it hits the mainstream.
And what's fascinating is that the papers we're looking at today touch on some really hot topics. AI, privacy, cybersecurity, all converging in ways we couldn't have imagined a few years ago.
Absolutely. We're seeing how AI is becoming a double-edged sword, capable of both launching incredibly sophisticated attacks and also forming the foundation of robust defenses.
A real cat and mouse game, it seems. So are you ready to dive in?
I am. Where do we even begin with all this cutting-edge tech?
Well, let's start with something that's been making headlines. Large language models, or LLMs.
Right.
Like ChatGPT, everyone's talking about them.
Right, and with that popularity comes concerns about privacy.
Exactly. So this paper, Deploying Privacy Guardrails for LLMs, caught my eye.
It's super relevant, especially with all the hype around ChatGPT and the potential risks of using these powerful AI models.
They actually tested this framework in real-world settings, which is pretty cool.
Yeah, they integrated it into a large data governance system and an open source platform. Pretty impressive results, I'd say.
What kind of results were we talking about?
Well, the framework achieved a 95% accuracy rate in detecting sensitive information across 26 languages. That's huge.
95%, wow. So even when you're using AI that's been trained on massive data sets, there's hope for keeping your personal data private.
There's definitely hope. It means we're moving in the right direction. Of course, more research is needed, but this is a promising start.
It is, especially with GDPR and all those data privacy laws getting stricter. Okay, what about this other paper? Towards Robust Multi-Tab Website Fingerprinting. The title itself sounds kind of creepy.
Yeah, this one's a bit unsettling. It highlights how attackers are finding ways to identify the websites you visit even when you think you're protected by encryption.
Wait, even with encrypted connections? So even using a VPN isn't a foolproof guarantee of anonymity anymore.
It seems not. This paper introduces the ARIS framework, which uses AI to analyze traffic patterns, and it's apparently very effective.
So what can you do to protect yourself?
Well, besides using a VPN, it's crucial to be mindful of the information you share online, especially on social media.
Right, and keeping your software updated. Those patches often include security fixes.
Exactly. Staying informed and being proactive is key. Now, let's move on to something that sounds straight out of a sci-fi film: intelligent attacks on cyber-physical systems and critical infrastructures.
Ooh, that sounds intense. Cyber-physical systems, we're talking about things that control our power grid, transportation, even healthcare, right?
Exactly. These are systems that have a physical component and a digital component. And this paper dives into how AI could be used to develop autonomous attacks on these critical systems.
Autonomous attacks,
Yeah.
like self-learning AI that can hack into these essential services.
That's the concern. It's a bit frightening to think about. Imagine an AI that can learn and adapt, finding new ways to exploit vulnerabilities and disrupt these critical infrastructures.
That's a pretty scary thought. It's like a real-life Skynet scenario.
Thankfully, the researchers also explore the potential of AI for defense.
Oh, so AI can be used to protect these systems too.
Absolutely. The paper discusses AI-driven mitigation strategies, basically using AI to detect and respond to these intelligent attacks.
So it's a constant race, with AI on both sides, constantly evolving and adapting.
It's a never-ending game of cat and mouse, but with much higher stakes.
Definitely higher stakes. Okay, let's switch gears a bit and talk about ransomware. It seems like we're hearing about a new ransomware attack every other week.
It's become a huge problem, affecting businesses, organizations, even individuals.
This next paper is titled Unveiling Zero-Space Detection, a novel framework for autonomous ransomware identification in high-velocity environments. The title itself is a mouthful.
It is a bit of a mouthful, but it essentially describes a new approach to detecting ransomware, using unsupervised clustering and deep learning.
Unsupervised clustering, deep learning.
Oh,
Could you break that down a bit for our listeners?
sure. Imagine this framework as an early warning system that can identify hidden behavioral patterns associated with ransomware attacks.
Okay, that makes sense.
These patterns might be missed by traditional detection methods, But this new framework can spot them even in high-velocity environments where data is coming in fast and furious.
So it's like having a super fast, super smart security guard that can spot suspicious activity even the busiest of places.
Exactly. And what's even more impressive is that the researchers tested it against a variety of ransomware families, including Lockbit and Conti, which are some of the most notorious out there.
Did it work?
It did. They achieved high detection rates with very few false positives, which is crucial.
That's good news. We need all the help we can get in the fight against ransomware. Now, this next paper might hit close to home for those of us in the cybersecurity field. Generative AI misuse potential in cybersecurity education. A case study of a UK degree program.
This one's interesting. It raises concerns about the potential misuse of generative AI, like ChatGPT, in cybersecurity education.
So students could potentially use AI to cheat.
That's one of the concerns. The paper highlights how a UK master's program in cybersecurity was found to be highly susceptible to misuse, especially when it came to project assessments.
So students could use AI to generate code or write reports without actually understanding the material.
Exactly. And that's a problem because it undermines the integrity of the education and could lead to graduates who lack the necessary skills and knowledge.
So what can be done about it?
The paper discusses the need for AI-resistant assessments, improved detection tools, and creating an ethical learning environment where students understand the implications of using AI in this way.
It's about striking a balance between leveraging the benefits of AI and ensuring that it doesn't become a shortcut to real learning.
Absolutely. Cybersecurity education needs to adapt to keep pace with these technologies, finding ways to incorporate them responsibly.
Now let's get into something a bit more technical. Analyzing and exploiting branch mispredictions in microcode. Sounds pretty hardcore.
This paper dives into the nitty-gritty of CPU vulnerabilities. It unveils a new class of vulnerabilities called USpectre.
USpectre. Is that related to the Spectre and Meltdown vulnerabilities we heard about a while back?
It is. These vulnerabilities exploit flaws in microcode, which is a deeper layer of software that controls the CPU.
So it's like finding a secret backdoor into the heart of the computer.
It's pretty serious. And what's even more interesting is that the researchers found that several previously known vulnerabilities, which were thought to be Spectre or Meltdown variants, are actually instances of USpectre.
So a whole new category of vulnerabilities with potentially serious consequences. Are there any defenses against these USpectre attacks?
The researchers propose USLH as a defense mechanism. But as always, it's a race against time.
I imagine as soon as a new defense is developed, attackers start looking for ways to bypass it.
Exactly. Cybersecurity is a constantly evolving field, and staying ahead of the curve is the name of the game.
Okay, let's shift our focus to a more theoretical approach to data protection. Statistical privacy. This sounds intriguing.
It's a bit different from traditional privacy models. It focuses on protecting data when an attacker knows the data's distribution, but not individual details.
So they know the general shape of the data, but not the specific values.
Right. Unlike differential privacy, which assumes the worst-case scenario, this model considers a more realistic attack model.
So it's a more nuanced approach to privacy, considering the specific context.
And they analyze how the entropy of the data distribution can help ensure privacy for certain types of queries.
Entropy, as in the measure of randomness or disorder.
Exactly. The more entropy in the data distribution, the harder it is for an attacker to extract specific information. That makes sense. So it's like adding noise to the data to make it harder to decipher.
It's a bit more complex than that, but you get the idea. They also provide formulas to calculate privacy parameters, which is useful for practical implementations.
All right, let's move on to a paper that tackles privacy in the context of machine learning. A selective homomorphic encryption approach for faster, privacy-preserving federated learning. Homomorphic encryption, that sounds pretty intense.
It is a powerful cryptographic technique. It allows you to perform computations on encrypted data without decrypting it.
So you can process data without ever actually seeing the raw data itself. That's pretty amazing.
It is. And this paper applies it to federated learning, which is a way to train machine learning models on data that's distributed across multiple devices without directly sharing that data.
So it's a way to collaborate and learn from data without compromising privacy.
Exactly. And their approach, called selective homomorphic encryption, only encrypts certain parts of the model, which improves performance without sacrificing security. So it's a balance between speed and security. Did their method work?
It did. They compared it to a method that uses fully homomorphic encryption and found it to be up to 90% faster.
That's a significant improvement. Selective homomorphic encryption could really pave the way for a wider adoption of privacy-preserving federated learning.
It has a lot of potential, especially in areas like healthcare, where data privacy is paramount.
Okay, let's move on to a paper that focuses on a key aspect of intrusion detection systems. Comparison of feature extraction tools for network traffic data.
This is all about finding the needle in a haystack. Feature extraction is the process of identifying meaningful features from network traffic data, which is essential for intrusion detection.
So it's like finding the telltale signs of malicious activity within a massive amount of data.
Exactly. And this paper compares different tools used for feature extraction, evaluating their accuracy and efficiency.
So it's like a buyer's guide for those building AI-powered intrusion detection systems.
You could say that. It provides valuable insights for choosing the most effective tools for the job, helping to make those systems more robust and reliable.
All right, let's dive into a paper that takes a multifaceted approach to security. Real-time multimodal subcomponent level measurements for trustworthy system monitoring and malware detection.
This one's about creating a more comprehensive security system by collecting measurements from various subcomponents of a system rather than just relying on the main processor.
So it's like having multiple eyes watching for suspicious activity, each with a different perspective.
Exactly. They propose collecting data from the network interface controller, the GPU, and other components, which gives a much richer picture of what's happening within the system.
So it's harder for malware to hide.
Much harder. By analyzing these multimodal measurements, you can detect anomalies and potentially malicious behavior that might otherwise go unnoticed.
It's like having a team of security experts, each specialized in a different area, working together to protect the system.
It's a very clever approach, and it highlights the importance of thinking outside the box when it comes to security.
Now let's talk about a paper that tackles the challenge of protecting personally identifiable information, or PII, in the age of LLMs. Adaptive PII mitigation framework for large language models.
This one's all about keeping your sensitive information safe when interacting with AI systems. They introduce an adaptive system designed to align with data protection regulations like GDPR and CCPA.
So they're building privacy protections into the very foundation of these LLMs.
Right, and their system uses advanced NLP techniques and context-aware analysis to identify and mask PII.
So it's like having a built-in privacy filter that can automatically redact sensitive information.
You could say that. And they tested it against existing tools and found it to be highly effective.
That's reassuring. We need solutions like this as LLMs become more prevalent in our lives.
Absolutely. It's about ensuring that we can leverage the power of AI without compromising our privacy.
Okay, let's move on to a paper that explores the world of adversarial machine learning. Robustness of selected learning models under label flipping attack.
This one's about testing how well different machine learning models can withstand attacks.
Adversarial attacks. What does that mean?
It's when someone intentionally tries to manipulate a machine learning model by feeding it corrupted data.
So like trying to trick the AI into making wrong decisions.
Exactly. In this case, they're looking at a specific type of attack called label flipping, where the attacker changes the labels of the training data.
So they're messing with the ground truth that the model learns from.
And they tested a variety of models, including traditional algorithms like SVM and random forest, as well as deep learning models like CNNs.
And what'd they find? Which models were the most resilient?
The multi-layer perceptron, or MLP, showed the best combination of accuracy and robustness against label flipping.
So it's a good choice for applications where security is critical.
Exactly. And this research is important because it helps us understand the vulnerabilities of different machine learning models and develop strategies to make them more robust against these attacks.
Okay, now for something a bit more cutting edge. Federated discrete denoising diffusion model for molecular generation with OpenFL.
Now, this one sounds like it's straight out of a science fiction novel. It combines federated learning with diffusion models to generate new molecules with desired properties.
Diffusion models, like those AI systems that can create realistic images from text prompts.
You got it. But instead of generating images, they're generating molecular structures.
So it's like AI-powered drug discovery.
That's one potential application. They used OpenFL, which is a federated learning framework, to protect the privacy of the training data.
So multiple research institutions could collaborate on drug discovery without sharing their sensitive data.
And what's even more exciting is that their model's performance was comparable to a model trained on centralized data.
So federated learning doesn't sacrifice accuracy. That's fantastic news for privacy-conscious applications.
It opens up a whole new world of possibilities for collaboration and innovation in fields like drug discovery and material science.
Okay, let's move on to a paper that addresses the ethical concerns of AI image generation. T2I safety, benchmark for assessing fairness, toxicity, and privacy in image generation.
This is a timely topic, given the increasing power and accessibility of AI image generation tools. This paper introduces a benchmark called T2I safety, which aims to evaluate these models for their potential to generate harmful or biased content, as well as their ability to protect privacy.
So it's like a set of standardized tests to assess the ethical behavior of these AI models.
Exactly. They developed a comprehensive taxonomy of tasks and categories related to fairness, toxicity, and privacy, and collected over 70,000 prompts for evaluation.
That's a lot of prompts.
Uh,
Did they find any concerning trends?
They did. They uncovered instances of racial bias in some models, a tendency to generate toxic content when prompted with certain words, and variations in how well different models protected privacy.
So even in the world of AI art generation, we're not immune to the biases and ethical dilemmas that plague human society.
Unfortunately not. This research highlights the need for ongoing vigilance and the development of safeguards to mitigate these risks.
It's a reminder that we need to be mindful of the potential downsides of these powerful technologies, even as we marvel at their capabilities.
Absolutely. It's all about responsible AI development and usage.
Okay, get ready for this next one. It combines two incredibly complex fields: practical quantum federated learning and its experimental demonstration.
This paper explores the intersection of quantum computing and federated learning. They envision a future where quantum computers, connected through a quantum internet, can collaborate and learn from each other without revealing their private data.
A quantum internet, that sounds like something straight out of Star Trek.
It's still in its early stages, but the potential is mind-blowing. And what's fascinating is that they successfully implemented their quantum federated learning framework on a 4-client quantum network.
A real quantum network. And did it work?
It did. They also conducted extensive simulations with up to 200 clients, and the results show that quantum federated learning can significantly improve model accuracy, especially when dealing with quantum data.
This research offers a glimpse into a future where quantum computing and AI converge to solve problems in ways we can barely imagine today.
It's a fascinating area, and it's only going to get more exciting as quantum technologies mature.
Okay, now let's talk about a paper that focuses on a specific type of attack targeting personalized federated learning. Bad PFL, exploring backdoor attacks against personalized federated learning.
This paper dives into the vulnerabilities of personalized federated learning, which we discussed earlier. It's where each user has their own private AI model trained on their data.
Right, like having a personal AI assistant that's unique to you.
The researchers developed a new type of attack called bad PFL that can inject backdoors into these personalized models.
Backdoors, so like hidden vulnerabilities that can be exploited later.
Exactly. And what's tricky about bad PFL is that it uses features from the actual data as triggers for these backdoors.
So the triggers are camouflaged within the data itself, making them incredibly difficult to detect.
It's a very sneaky approach, and what's concerning is that they tested their attack against a variety of PFL methods and found it to be very effective.
So even personalized AI systems are not immune to these sophisticated attacks.
It highlights the ongoing challenge of securing AI, especially as we move towards more personalized and distributed systems.
It's a reminder that we need to be proactive and develop robust security measures to mitigate these evolving threats.
Absolutely. Staying ahead of the curve is essential in the world of cybersecurity.
All right, let's dive into a paper that explores the theoretical limits of privacy in the quantum realm. Impossibility of quantum private queries.
This one delves into the fundamental trade-offs between user privacy and database security when it comes to retrieving information from a database without revealing the specific information being sought.
So it's like trying to search for something anonymously, but also ensuring that the database itself remains secure.
And the researchers proved that it's impossible to achieve both perfect privacy for the user and perfect security for the database in the context of quantum private queries.
So there's always going to be some degree of compromise.
It seems so. This research has significant implications for designing secure quantum communication protocols.
It underscores the need to carefully consider the trade-offs between privacy and security, especially as we venture into the uncharted territory of quantum information processing.
It's a reminder that even with the most advanced technologies, there are fundamental limitations we need to be aware of.
Okay, 2 more papers to go. Let's explore one that focuses on refining the capabilities of LLMs as content judges, refining input guardrails. enhancing LLM as a judge efficiency through chain-of-thought fine-tuning and alignment.
This paper builds on the idea of using LLMs for content moderation, which we discussed earlier. It dives into how to make LLMs more efficient and reliable at detecting and filtering out potentially harmful or inappropriate content.
That was about training LLMs to be better judges of what's acceptable and what's not.
Exactly, and they focus on refining the chain of thought responses of these models.
Chain-of-thought responses, you mean where the LLM explains its reasoning step by step?
You got it. By fine-tuning and aligning these chain of thought responses, they aim to improve the LLM's ability to identify and reject harmful input while providing transparent explanations for its decisions.
It's about making the decision-making process more transparent and understandable.
And they found that these techniques significantly enhance the safety and reliability of LLMs as content moderators, even with limited training data.
That's a promising step towards building more trustworthy and responsible AI systems.
Definitely. Transparency and explainability are crucial for building trust with AI.
All right, last but not least, let's explore a paper that tackles privacy concerns in the realm of location-based services. HLPS, a hybrid approach for users' location privacy in location-based services.
This paper proposes a new approach to protecting user location privacy while still allowing them to enjoy the benefits of location-based services.
It's a delicate balance, isn't it? Location data is incredibly valuable, but it's also highly sensitive.
Their solution, called HLPS, stands for Hybrid Location Privacy Scheme. It combines two techniques, obfuscation and user collaboration.
Obfuscation, that's like intentionally making your location data less accurate to protect your privacy.
Exactly. It introduces some uncertainty into your location, making it harder for someone to pinpoint your exact whereabouts.
But doesn't that make location-based services less useful?
That's where user collaboration comes in. HLPS allows users to share more precise location data with specific people or groups they trust.
So you can choose who gets to see your exact location while still enjoying the convenience of location-based services.
It's a win-win. And they found that HLPS offers high levels of privacy while maintaining good accuracy for most users.
That's encouraging. It seems like HLPS could be a promising solution for enhancing location privacy in various applications.
It has a lot of potential, especially as we become more reliant on location-based services in our daily lives.
Okay, let's take a breather. We've covered a lot of ground today, from AI-powered attacks to quantum cryptography to privacy-preserving machine learning.
It's amazing to see the breadth and depth of research happening in the world of cybersecurity.
It's a constant race to stay ahead of the threats, but it's also incredibly exciting to see these innovations emerge.
Absolutely. And the key takeaway for me is that we need to stay informed, be proactive, and think critically about the technologies we use and the data we share.
It's about being aware of the risks and taking steps to protect ourselves, both as individuals and as a society.
And that's what cybersecurity is all about, staying vigilant and evolving alongside the ever-changing landscape of technology. It's mind-boggling how central AI is becoming to both cyber offense and defense. It's like a tech arms race where each side is constantly pushing the boundaries.
Yeah, it's exciting and kind of unsettling at the same time. To see AI's potential for both good and bad, like those sophisticated attacks, but also, building those super robust defenses.
Yeah.
Understanding AI and its implications is really key for anyone in cybersecurity, right?
Oh, absolutely. But let's move on, shall we? What about that paper on the matching arrangement of a graph? Improper weight function problem and its application. I'm kind of curious about that knapsack-like public key crypto system you mentioned earlier.
Oh, yeah. That one was interesting. They're connecting graph theory and cryptography.
So like visual representations of networks and how they can be used to secure information.
Exactly. They focused on something called a matching arrangement of a graph.
Okay, help me visualize this.
So imagine a network with points connected by lines, and you have to pick specific lines so no two lines share a point. It's about finding a unique set of connections.
Okay, I get that. But how do you jump from lines and points to encryption?
Well, that's where those improper weight functions come in. It's kind of like assigning different values or weights to these lines. They use this setup to create, get this, a public key crypto system.
It's like building a digital lock and key based on these matching arrangements.
Precisely. The public key locks or encrypts the message, and only someone with the private key can unlock it.
That's pretty cool. Using these abstract mathematical concepts to create practical tools for secure communication.
It really highlights how unexpected ideas can lead to amazing breakthroughs. Okay, ready for a quantum leap? Let's talk about parallel remote state preparation for fully device-independent, verifiable blind quantum computation.
Wow, even the title is a mouthful. Quantum computing always feels like we're stepping into the unknown.
It definitely does. But it's a future we can't ignore. This paper's all about ensuring the privacy and accuracy of quantum computations.
So imagine you need to do some super complex calculations on a quantum computer, but you don't own one or don't fully trust the one you have access to.
Yeah, that's a real worry. Like, what if they're manipulating the data or spying on the results?
And that's where device-independent, verifiable blind quantum computation comes in, thankfully. They call it VBQC.
Okay, I'm already lost. VBQC.
Basically, it lets you delegate quantum computation to someone you don't necessarily trust without revealing any details about what you're calculating, and you still get accurate results.
Wait, so they're doing the calculations for you, but they have no idea what they're actually doing.
Pretty much. And to achieve this mind-blowing feat, they use something called parallel remote state preparation.
Hold on, state preparation. What does that even mean in this context?
Think of it as setting up the quantum bits on the remote computer without revealing the actual instructions or information encoded in those bits.
Okay, so that's how they hide the details of the computation. But how do they ensure it's done correctly?
That's the verifiable part of VBQC. There are clever ways to check the results without needing to know the specifics of the computation. It's like having a guarantee that the server is doing its job right without giving it the blueprints.
Wow, that's seriously impressive. Quantum cryptography is like a whole other level of complexity. Let's bring it back down to earth a bit and talk about RAG with differential privacy. It addresses privacy concerns related to those large language models we discussed earlier.
Ah, yes, those powerful LLMs that are both impressive and potentially risky. They can be amazing tools, but there's always the danger of them revealing sensitive information.
Right, like accidentally leaking private details from the massive data sets they're trained on. How does this paper propose to solve that?
Well, it focuses on retrieval augmented generation, or RAG.
RAG, okay. What is that?
It's basically a way to supercharge LLMs by giving them access to external information. Think of it as connecting an LLM to a giant library.
So they're not limited to what they've been trained on.
Exactly. But this is also where the danger lies. What if those external sources contain private or sensitive information?
Oh, I see the problem. It's like giving the LLM access to confidential files. You don't want it spilling the beans.
Exactly. So, to protect that information, they use differential privacy. It's a way to ensure that the LLM's responses don't reveal anything about the specific data they were trained on.
So they can still give informative answers, but without jeopardizing anyone's privacy.
It's like adding a layer of privacy protection, scrambling the information in a way that makes it impossible to reconstruct the original sensitive details.
That's reassuring, especially as LLMs become more integrated into our lives. Okay, on to a more technical topic. Introducing Perturbability Score, PS, to enhance robustness against problem space evasion adversarial attacks on flow-based ML-NIDs. This one's about defending our networks, right?
Yeah, it's a deep dive into the world of machine learning-based intrusion detection systems.
ML-NIDS. Okay, so these are like the security guards of our networks, constantly watching for any suspicious activity.
Pretty much. They analyze the network traffic looking for patterns that might indicate an attack. But these systems aren't foolproof. Attackers are always finding new ways to bypass them.
So it's a constant game of cat and mouse, with both sides trying to outsmart each other.
Exactly. This paper focuses on a specific type of attack called problem space evasion attacks.
Problem space evasion, huh? That sounds complex.
Imagine an attacker manipulating the network traffic to make it look harmless so it slips past the MLNIDs.
Oh, like disguising themselves as a friendly visitor? That's sneaky.
To combat this, the researchers came up with the Perturbability Score, or PS.
The PS, okay. And what does it do?
It essentially measures how vulnerable each feature in the MLNIDS is to manipulation. It's like assigning a vulnerability rating to different parts of the system.
So features with high PS scores are the weak spots, the ones that attackers could exploit.
Exactly. And by focusing on features with low PS scores, the ones that are hard to manipulate, we can make the system more robust.
It's like reinforcing the walls were the weakest.
Right. And the best part is they found that by using this approach, they could significantly reduce the system's vulnerability without sacrificing its ability to detect actual attacks.
That's great news. It's encouraging to see researchers developing innovative solutions to protect our networks as these threats evolve. Speaking of evolving, let's talk about the dark side of a seemingly utopian concept: mapping the DeFi crime landscape. an evidence-based picture. Decentralized finance, it's all about transparency and cutting out the middleman.
That's the idea, at least. But as with any new technology, it attracts those looking to exploit it. This paper takes a close look at the crimes happening in the DeFi space.
I'm actually really curious about this. DeFi is all about removing central control, which seems like it could make it a haven for criminal activity.
That's a valid concern, and the researchers found some interesting patterns. They analyzed over 1,000 crime events between 2017 and 2022. Their findings show, get this, the very people developing DeFi technology are often both the victims and the perpetrators.
Wait, so the ones building this system are also the ones being targeted and exploiting it?
That's right. It's kind of like a double-edged sword.
I'm surprised. What are the most common DeFi crimes?
They found two main categories. First, attacks targeting those developing DeFi, often exploiting technical vulnerabilities in the code, which leads to major financial losses. And second, malicious activities by those same developers, like those rug pulls we talked about.
Rug pulls. I think I missed that one.
Imagine a DeFi project's developers suddenly disappearing with all the invested funds.
Like an elaborate exit scam? That's pretty disheartening. And I imagine with DeFi's decentralized nature, it's hard to track these criminals down.
It is. There's no central authority, and often transactions involve pseudonyms, which makes it really difficult to trace the money or hold those responsible accountable.
So it's a wild west out there in the DeFi world.
In a way, yes. The researchers emphasize the need for rigorous security audits, code reviews, and constant vigilance to prevent exploits. And of course, increased transparency and accountability are crucial for building trust.
It's a balancing act, isn't it? Fostering innovation while also protecting users from harm. Okay, let's get technical again with implementation study of cost-effective verification for Petersak's verifiable delay function in Ethereum smart contracts.
This paper focuses on a specific type of function called a verifiable delay function, or VDF.
A VDF, what that?
It ensures a minimum delay before a computation can be completed, even with enormous computing power.
So it's like a time lock that prevents things from happening too quickly.
Exactly. They have all sorts of uses in blockchain technology, like generating random numbers, selecting leaders for consensus, and even preventing certain types of attacks on decentralized exchanges.
Okay, I'm starting to see the potential here. But how do they actually work in practice?
This paper focuses on optimizing the verification process for Petersak's VDF, specifically on the Ethereum virtual machine where smart contracts run.
So they were trying to make it more efficient.
Right. They managed to significantly reduce both the computational cost and the size of the proof needed for verification. This is a big deal because it makes VDFs more practical for real-world blockchain applications.
That's a win for blockchain security. Now let's jump to HLPS, a hybrid approach for users' location privacy in location-based services. This sounds like it hits close to home. We're all using location-based services these days.
Location data is valuable, but it's also really sensitive. This paper introduces HLPS, or Hybrid Location Privacy Scheme, to address this issue.
Hybrid, so it combines different approaches.
Exactly. It uses both obfuscation techniques, which introduce uncertainty into location data, and user collaboration.
Obfuscation, that's like intentionally making your location data less accurate to protect your privacy, right?
Exactly. But to avoid compromising the usability of location-based services, they also incorporate user collaboration.
So you get to choose who sees your precise location while still being able to use those services.
Precisely. Users have more control, and the system performs well, offering high levels of privacy without sacrificing accuracy. It's a promising solution for enhancing location privacy across various applications.
It's encouraging to see researchers developing these kinds of solutions. Let's move on to refining input guardrails, enhancing LLM as a judge efficiency through chain of thought, fine-tuning, and alignment. LLMs as judges, that's an interesting concept.
This paper focuses on using LLMs for content moderation, but with an emphasis on refining their ability to make sound judgments and explain their reasoning.
So it's not just about filtering content, it's about making sure they're doing it for the right reasons and in a transparent way.
Exactly. They're working on improving the LLM's chain of thought responses.
Chain of thought. So like explaining step by step how they reached a decision.
Right. Making their thought process visible so we can understand and trust their judgments.
It's like having the LLM show their work, so we can see they're not just blindly following instructions.
And their research shows that this approach is effective. Fine-tuning and aligning those chain of thought responses significantly improves the LLM's ability to filter out harmful content, even with limited training data.
That's great. Transparency and explainability are essential for building trust with any AI system, especially one that's making decisions about what we see and hear. Our last paper for this segment delves into a bit of a mind-bending concept: impossibility of quantum private queries.
This one explores the boundaries of privacy in the quantum realm.
Quantum private queries. Can you break that down for me?
It's all about retrieving information from a database without revealing what you're searching for.
Okay, so it's like a super secure way to access information without leaving a trace.
In theory, yes. But the researchers discovered a fundamental limitation.
Oh, there's a catch.
It turns out that in the quantum world, you can't have perfect privacy for the user and perfect security for the database at the same time.
So if you want to keep your search completely private, you risk compromising the security of the entire database.
That's what their research suggests. It's a fundamental trade-off that we have to grapple with as we develop quantum technologies.
It's a reminder that there are limits, even in the quantum world. Welcome back to the Deep Dive. We've been exploring all sorts of fascinating research, and now we're diving into a paper that caught my eye. Bad PFL, exploring backdoor attacks against personalized federated learning. I mean, it sounds kind of malicious and personal at the same time, which seems odd.
It is a bit of a strange combination, but this paper looks at the vulnerabilities of personalized federated learning, PFL for short.
PFL, okay.
It's like regular federated learning, but each user has their own separate model, trained just on their data, like having a personal AI assistant but without sharing your data.
Oh, I see. So it's more privacy-focused. But where's the bad come in?
Well, the researchers figured out a new type of attack. They call it bad PFL. It takes advantage of that personalized structure.
So regular attacks wouldn't work against PFL.
Not so well. Those traditional backdoor attacks where you sneak malicious code into a model, they don't really stick with PFL because each user has a unique model.
So how does this bad PFL thing work then?
It's clever, actually. They use features from the actual data itself as triggers. Those triggers get embedded during training, so they become part of the model, hard to spot.
So it's like the attack is hidden in plain sight, disguised as normal data. That's really sneaky. Can you defend against something like that?
That's the problem. They tested it against all sorts of PFL methods, even ones with good defenses, and it was still really successful. It shows how tricky it is to keep these personalized AI systems secure.
It's a good reminder that as AI gets more personalized, security needs to keep up. Speaking of advanced tech, let's look at practical quantum federated learning and its experimental demonstration.
Quantum computing and federated learning, they're bringing two cutting-edge fields together. Imagine quantum computers working together but without actually sharing their data.
That sounds like the best of both worlds. Incredible processing power and strong privacy. But how do you even test something like that?
They actually built a small quantum network, just 4 clients, and they ran their framework on it. And get this, it worked.
A real quantum network. That's amazing.
They also ran simulations on larger networks, up to 200 clients, and their results are really promising. Quantum federated learning could be a game changer for tasks that need that quantum advantage, and it keeps data safe too.
It's like a glimpse into a future where we can harness the power of quantum computing without sacrificing privacy. Okay, let's switch gears again with impossibility of quantum private queries. It sounds a bit ominous.
This one is a bit heady, but it gets to the heart of privacy in quantum information. They're looking at whether you can get information from a database without revealing what you're looking for.
Like an ultra-private search. I can see why that would be useful.
Right, but there's a catch. They proved that in the quantum world, you can't have perfect privacy for the user and perfect security for the database at the same time.
So, you have to choose one or the other.
It seems that way. If you want to hide your search completely, you risk making the whole database vulnerable.
That's a tough trade-off. It shows the complexity of designing secure systems in this new quantum era. Okay, let's talk about something a bit more down to earth. T2A safety. Benchmark for assessing fairness, toxicity, and privacy in image generation. This is about those AI image generators that everyone's using, right?
Exactly. T2I safety is a benchmark for evaluating those text-to-image models, looking at how fair, safe, and private they are.
It's like a standardized test to make sure these AI models are behaving ethically. So how do they do?
Well, there were some concerning findings. They found instances of bias, the potential to generate harmful content, and variations in privacy protection.
So even in the world of AI art, we're dealing with real-world ethical issues. It's a reminder that we need to be cautious and develop safeguards as this technology advances. Okay, on to the next paper. Refining input guardrails. enhancing LLM as a judge efficiency through chain-of-thought fine-tuning and alignment. This is about improving the content moderation capabilities of LLMs, right?
It is. They're trying to make LLMs more efficient and reliable at filtering out harmful or inappropriate content.
So it's not just about blocking stuff. It's about making sure the LLM is making good decisions.
And they do that by focusing on those chain of thought responses.
Right, where the LLM explained its reasoning.
They found that refining and aligning those responses makes a big difference. The LLM becomes a better judge, even with limited training data.
It's like teaching the AI to think critically and justify its actions. That's crucial for building trust and transparency. And that brings us to our final paper. HLPS, a hybrid approach for users' location privacy in location-based services. We're back to location privacy, it seems.
Location data is so valuable, but it can be misused. This paper tries to find that sweet spot between utility and privacy.
So how does HLPS achieve that balance?
It uses a hybrid approach, combining obfuscation, which makes location data less precise, with user collaboration.
So you can choose to share your exact location with people you trust, but keep it hidden from everyone else.
That's the idea. And it seems to work well. They found it offers good privacy without sacrificing accuracy.
That's a promising solution for location-based services. And that wraps up our deep dive into the world of cybersecurity research. We've covered a lot of ground today, from backdoor attacks and quantum computing to ethical AI and location privacy.
It's been a fascinating journey exploring these cutting-edge advancements and emerging threats.
It's clear that cybersecurity is a constantly evolving field, and staying ahead of the curve is essential. So thanks for joining us on the deep dive. Stay vigilant, stay curious, and stay safe out there in the digital world.